Welcome to Corner e-learning course Ultrasonic Flow Meters for Measuring Liquids in Closed Processes. This course will give you an overview into the measurement technology and tell you all the main features and properties. The course consists of 3 structured parts. Before we go deeper into the subject, let's look briefly at our learning targets in this learning module. At the end of this module, you will have an overview of ultrasonic measurement and its historical development. You will have learnt the terms velocity of sound, sound wave, frequency of sound, as well as the measuring principle and the operating mode of ultrasonic flow meters. So now, let's get started. We can look first at the historical development of ultrasonic flow measurement. The use of ultrasound in flow measurement began in the last century, when in the 1920s Oscar Rutten patented his method and apparatus for measuring the volume of flowing liquids, gas, and steam. The first ultrasonic flow meters were introduced in the 1950s, and in the 1960s different companies developed the first ultrasonic flow meters using the differential transit time method. At this time, the first clamp-on ultrasonic flow meter was also launched onto the market. Corner has been developing inline ultrasonic flow meters since the end of the 1970s. The first multipath ultrasonic flow meters for measuring gases were finally introduced at the start of the 1980s. However, the main breakthrough in ultrasonic flow measurement has come in the last 10 to 20 years, which have seen the breakthrough of digital measurement. The exact recording and analysis of transit times has become increasingly accurate, which of course has made the measuring device extremely interesting to industry. Today, there are several different technologies on the market for ultrasonic flow measurement, with a wide range of applications. But how does ultrasonic flow measurement function today? What should we know, and what are the essential characteristics? In order to understand the measuring principle itself, we should first become acquainted with some basic terms which are important in ultrasonic measurement. Frequency and velocity of sound. Ultrasound, which is also called audible sound, consists of oscillations which move in a medium at a certain speed. Frequency and amplitude. For sound to propagate, a medium is needed whose molecules can transport the sound. If we picture a vacuum, we know from experience that since there is no sound there can be no propagation of the sound waves. One of the properties of a medium is the speed at which sound propagates in it. At a specific temperature, every medium has its own specific sound propagation velocity, which is also known as the speed of sound. The denser the molecular structure of a medium, the faster the sound waves propagate in the medium, and the higher the velocity of sound of the medium. From this we can deduce that the velocity of sound of solids is greater than that of liquids, which in turn is greater than the velocity of sound of gases. One example from everyday life is an approaching train. The sound of the approaching train is perceived more quickly over the rails than through the air. Let's look at some examples at a temperature of 25 degrees C. These examples only apply at 25 degrees C because, when there is a change of temperature, the velocity of sound changes too. At a temperature of 25 degrees C, air has a velocity of sound of 346 meters per second, methane 430 meters per second, and helium 965 meters per second. As we've already seen, the velocity of sound in liquids is usually higher than in gases. Water has a velocity of sound of 1,497 meters per second, and glycol 1,658 meters per second. Solids and particulate materials have even higher velocities of sound. Plastic or PVC 2,400 meters per second. titanium 3,125 meters per second, and carbon steel 3,230 meters per second. Sound waves can propagate in media in different ways. We can start by looking at the longitudinal wave. This is a physical wave which oscillates in the direction of propagation. It always needs a medium in order to move. The best known example is sound in the air or in water. Longitudinal waves are pressure waves. This means that in a medium, zones with gauge pressure or compressive stress, low pressure or tensile stress move or travel in the propagation direction. The individual particles in the medium, atoms or molecules, oscillate in the direction of propagation. When the oscillation has passed, the particles return to their rest position, the equilibrium position. No energy is lost when the oscillation is propagated, apart from the losses due to the friction between the particles. The counterpart to the longitudinal wave is the transverse wave, which is also known as a shear or bending wave in solids. A transverse wave is a physical wave in which oscillation is perpendicular to the direction of propagation. In contrast to longitudinal waves, not all types of transverse wave are restricted to one medium. In gases and liquids, ultrasound propagates only as a longitudinal wave, or in other words, longitudinal waves compress and decompress the medium in the direction of the propagation. Another important term in ultrasonic measurement is frequency of sound. As we've already seen, in a given material, sound always propagates at the same speed at a certain temperature. According to the following equation, the wavelength of sound is directly proportional to the velocity of sound and, inversely, proportional to frequency. So we obtain wavelength lambda is equal to velocity v divided by frequency f. The frequency of sound is measured in hertz. The human ear can hear up to a range of 18 to 20 kilohertz. Above 20 kilohertz we talk about ultrasound, which can no longer be perceived by the human ear. Some animals, however, can hear higher frequencies, as we can see in the slide. Ultrasonic flow meters operate in an even higher frequency range. Since from frequencies of 1 or 2 megahertz, there is no longer any acoustic interference like that which valves or pumps can cause in industrial plants. So we can apply the following rule of thumb. The lower the velocity of sound of a medium, the lower the frequency with which ultrasonic flow meters work. In applications to measure liquids, the frequency is from 2 megahertz down to 500 kilohertz. Among other things, this also depends on the viscosity of the medium being measured. Frequencies between 500 kHz and 80 kHz are used in applications which measure gases. Different frequencies affect the penetrating power in the media, the shape of the acoustic beam, and the divergence of the acoustic beam. The excitation voltage and the pulse length of ultrasonic sensors can also vary. Now we've got to know some of the basic terms needed to understand ultrasonic flow measurement, we can move on to the measuring principle itself. There are two different technologies in ultrasonic flow measurement: the Doppler effect and determining the flow using the transit time difference. We can start with the Doppler effect. The Doppler effect is the change perceived or measured in the frequency of any kind of wave when the source and the observer approach or move away from each other. In other words, when they move relative to one another. When observer and source approach each other, the frequency perceived by the observer increases, but then drops again when they separate. One well-known example of this is the change in pitch of an ambulance siren, where only a frequency shift takes place. A Doppler ultrasonic flow meter works on this principle. The transmitter frequency changes linearly when it is reflected by particles and gas bubbles in the medium. The net result for the Doppler ultrasonic flow meter is a frequency shift between the Doppler signal transmitter and the signal receiver, In other words, we nominally receive a difference in frequencies. This difference in frequencies is proportional to the flow rate. When the nominal diameter of the pipe is known, we can also calculate the volume of the flow. The measuring principle requires a minimal amount of solid particles or air in the medium to achieve optimal measurement results. These are called reflectors. Ultrasonic flow meters, which measure according to the Doppler effect, are clamp-on ultrasonic flow meters and are particularly suited to applications with very dirty water or slurry. However, they never measure as accurately as ultrasonic flow meters using the differential transit time method. So we should move on to this method, which is very widely used in industry. Ultrasonic flow measurement with the transit time difference is based on one simple physical fact. Imagine two canoes crossing a river diagonally on the same line, one in the direction of the flow and the other against it. The canoe moving in the direction of the flow needs considerably less time to reach the other riverbank than the canoe moving against the direction of the flow. If we transfer this concept to the measuring principle, we can see that ultrasonic waves along a diagonal path behave in exactly the same way. A sound wave propagates in the direction of the flow of the medium, such as a liquid or a gas, more quickly than a sound wave propagating against the flow direction of the medium. The difference in the transit time is directly proportional to the flow velocity of the medium. In order to understand the technical background, but without going too deeply into the construction of an ultrasonic flow meter, we can look at the most important features. The transducers, which are always in pairs and mounted under an angle, consist of a transmitting and a receiving transducer, which we can call transducer A and transducer B. The two transducers act both as signal transmitter and signal receiver. The time an acoustic wave needs to travel from transducer A to transducer B, that is in the flow direction of the medium, is known as transit time TAB, and from transducer B to transducer A, that is against the flow direction, TBA. The transit times TBA and TAB are measured continuously. The difference in transit time TBA to TAB is directly proportional to the average flow velocity, Vm, of the medium. Let's see why ultrasonic flow measurement is completely independent of the medium. As we can see in equation 1, the transit time of a signal is the distance between transducer A and transducer B, divided by the velocity which the acoustic signal needs to travel from one transducer to the other. Equations 2 and 3 describe the time the acoustic signal needs from transducer A to transducer B, and from transducer B to transducer A. The transit time of the signal is measured and then used with other variables to calculate the flow. Although the signal travels in a straight line, it is traveling at an angle, alpha, to the pipe axis. Equations 2 and 3 define the flow rate between transducer A upstream and B downstream. The transit time is shorter when the acoustic signal is transmitted downstream, that is in the direction of the flow of the medium, equation 2, than when it is transmitted upstream, that is against the direction of the flow, equation 3. The transit times are measured in rapid succession, tens of times a second. In practice, we can assume that since neither the temperature, nor the pressure, nor the composition of the medium will change in these intervals, that is within milliseconds, they remain constant. So, during the transit time period, the velocity of sound can also be seen as constant. Assuming then that neither temperature, pressure, nor composition of the medium change in such a short time, the resulting flow rate of the medium can be shown as follows. The length of the acoustic path divided by 2 times the cosine of alpha multiplied by the result of dividing the difference between the two transit times by the product of the two transit times. Equations 2 and 3 combined result in the formula path length divided by 2 cos alpha multiplied by the transit time. This represents the average flow velocity. When multiplying the average flow velocity with the cross-section of the pipe, we get the flow rate Q. The cross-section of the pipe is constant for an inline ultrasonic flow meter with a diameter d and transducers, which are welded into the spool piece at a fixed angle alpha. These formulas confirm what we've already seen, that is, that the characteristics of the medium do not affect the measurement. These characteristics include density, temperature, pressure, and the velocity of sound of the medium. If we rewrite the formulas a little, we can see that the velocity of sound can be calculated using differential transit time. During calibration, the path length L is very accurately defined and is therefore known and fixed. The velocity of sound is the path length times 2 divided by the sum of the two transit times TAB and TBA. At a typical velocity of sound of 1,500 meters per second, the accuracy achieved is plus or minus 0.5 meters per second. This gives ultrasonic flow measurement a unique feature. Because the path length and the measured transit times are fixed, the velocity of sound is available as a measured value. The velocity of sound of a medium can be used for diagnostic purposes, for example, to identify a product such as oil. The diagram shows the identification of different types of crude oil. Identifying the velocity of sound can be useful in a tank farm, for example, where ships unload a variety of crude oils. These oils can differ according to their source. This means that crude oil can have different velocities of sound, between 800 and 1,500 meters per second. Crude oil A, for example, with a velocity of sound of 1,330 meters per second at 20 degrees C, is being unloaded into tank X. As soon as the ultrasonic flow meters measure a velocity of sound of 1,420 meters per second, the control room knows that crude oil B is flowing through the pipe, and the valve can be switched from open to closed. Let's summarize briefly what we've learned in this module. Following a short overview of the historical development of ultrasonic flow measurement and an explanation of some important terms such as velocity of sound, sound wave, frequency of sound, we discussed the measuring principle and the main operating mode of ultrasonic flow meters. Besides the Doppler effect, which only plays a minor role in ultrasonic flow measurement, we became familiar with the differential transit time method, which is widely used in industry and which we went into in depth. Let's continue now in the second module with the construction and functions of an inline transducer. Welcome to the second part of the Corner e-learning course, Ultrasonic Flow Meters for Measuring Liquids in Closed Processes. To understand the subject matter better, you should have already completed the first module. Let's look first at the learning targets in this module. Upon completion of this module, you'll be able to describe the construction and functions of an inline transducer for measuring liquids, and as well as knowing the important physical basics of the measuring principle. You will have learned the different arrangements of measuring paths which are found in ultrasonic flow measuring technology, and you'll be able to explain their advantages and disadvantages and have a good overview of the different measuring accuracy levels. You will also be familiar with the calibration of ultrasonic flow meters for liquids. Now that we've studied the main operating mode of ultrasonic flow meters for liquids, we can take a closer look at the construction of an inline ultrasonic flow meter. Inline ultrasonic flow meters can have different diameters, from DN25 up to DN3000. Different versions of transducers can be applied for various applications, and also the different pipe sizes. The measuring tube is made of steel or stainless steel. In this case, we only want to study the construction and functions of a transducer in an inline ultrasonic flow meter for liquids. The two most important functions of a transducer are to generate and receive acoustic signals in order to measure the transit times of the ultrasonic signal. This function is performed by a piezo crystal built into the transducer. The piezo crystal converts an electrical voltage into a sound pulse, and vice versa, a sound pulse into an electrical voltage. So there must be at least two transducers, which can be operated both as signal transmitter and receiver. The control electronics then decides which transducer has which function. The piezo crystal is an important part of the transducer. It's able to convert an electrical voltage into acoustic signals and vice versa. The transducer window protects the piezo crystal, so the liquid measured in the pipe only comes into contact with this window. The transducers are welded into and slightly retracted from the pipe wall, called pockets. The flow of the medium produces small vortices in these pockets, which keep the transducers clean. An electrical pulse is passed through the piezo crystal in transducer A. The piezo crystal emits an acoustic signal, which is sent through the window into the measuring tube. The piezo crystal actually emits an acoustic signal in all directions. But the acoustic shield stops transmission back into the transducer, but the transducer window allows transmission of the strong focused bundle. This signal is received by transducer B, diagonally opposite, converted by the piezo crystal into an electrical signal, and processed in the converter. Since the distance between the two sensors is known, the speed of the acoustic signal can be calculated. Then an electrical pulse is passed through the piezo in transducer B. This in turn sends an acoustic signal to transducer A. The signal is detected by the piezo crystal, converted into an electronic signal, and processed in the converter. As we've seen, the time difference between the two immediately consecutive measurements is proportional to the flow velocity of the medium. For inline ultrasonic flow meters, the cost depends on the spool piece itself plus the transducers. The material selection is straightforward because metal is in contact with the liquid only. As a result, engineering is easy, and solutions for high pressure ratings and for high process temperatures are available. When the liquid to be measured is extremely hot, the piezo crystal must be protected from the high temperature. This is achieved using a waveguide which isolates the piezo crystal physically from the hot medium. The waveguide is made entirely of solid stainless steel. This means that temperatures of up to 500 degrees C can be measured. Two examples of this are bitumen and the thermal oil used in parabolic trough power plants, but also boiler feed water and many others. In order to understand the measuring principle and the construction of an ultrasonic flow meter, we must also familiarize ourselves with some of the properties of a medium itself. Media can be split into multi-phase and single-phase. We will concentrate only on single-phase media and specifically liquids. Liquids can be divided into two groups, Newtonian and non-Newtonian liquids. Newtonian liquids are liquids which only change their viscosity when there is a change in temperature. Newtonian liquids are, for example, water and many oils. These liquids are well suited to ultrasonic measurement. As opposed to a Newtonian liquid, a non-Newtonian liquid is a liquid whose viscosity does not remain constant when the shear forces change. So this fluid does not conform to the Newtonian law of fluid friction. A few examples of non-Newtonian liquids are blood, cement pastes, starch water suspensions, lubricants, polymer melts, or ketchup. We will only study single-phase media, and only Newtonian liquids which can be measured by ultrasonic flow meters. We can move on now to some important physical basics of the ultrasonic flow measurement of liquids. These include density, viscosity, and the Reynolds number, which describes the flows in pipelines. We can start by looking briefly at density. The density of liquids can be seen as constant, and it is very difficult to change the density of a liquid through a temperature and/or pressure change. By programming the constant density in the flow converter, ultrasonic flow meters can measure both volumetric flow or mass flow. Volume times density is mass. Viscosity is the resistance of a liquid to flowing. Viscosity is very important in ultrasonic flow measurement. Viscosity results from the internal friction of the particles. When the viscosity increases, the material becomes thicker. We can look at an example of this. Water has a lower viscosity than crude oil. Viscous liquids flowing through a pipe cling more to the tube wall, and so the flow rate at the pipe wall is lower than in the center of the pipe. We distinguish between dynamic viscosity and kinematic viscosity. The factor between the dynamic and kinematic viscosity is the density of the material. Details of dynamic viscosity can sometimes also be seen in centistokes, where 1 centistokes is 1 millimeter squared per second. When the temperature of a liquid rises, the viscosity sinks. One example from everyday life is a car engine. When the engine is still cold, the engine oil is thick, or in other words, viscous. After driving a few kilometers, the engine and the oil have warmed up, and the oil becomes thinner, less viscous, and it flows more easily. It is also important to know the Reynolds number, which results from the viscosity we saw earlier. This is a dimensionless number and describes more exactly the flows in pipelines. Using the Reynolds number, we can distinguish between laminar and turbulent flows. This can be seen in the different velocity distribution in the cross-section of the pipe. Laminar flows have a parabolic profile, whereas turbulent flows have a flat profile. Since we cannot see the velocity distribution in closed pipes from the outside, we use the Reynolds number to determine which flow is present. The Reynolds number is average speed, V, multiplied by the cross-section of the pipe, D, divided by the kinematic viscosity. In order to distinguish the two flow profiles, we can say, if the value obtained is below 2,320, we talk about laminar flow. Everything above is known as turbulent flow. A medium between 2,320 and 4,000 is situated in the transition zone. This is an extremely unstable area in which the flow profile is not clear, so it is very difficult to get stable readings. A turbulent flow profile is defined as a Reynolds number above 4,000. Now we have learned the main physical basics, we can move on to the accuracy of this measuring principle, which is connected to the Reynolds number, and also to the number of acoustic paths of an ultrasonic flow meter. Let's look at an idealized model. In an ultrasonic flow meter with a single path, we measure through the center of the pipe, so the measurement result depends heavily on the flow profile. This affects laminar flow profiles in particular, in which the flow velocity in the center of the pipe is higher than nearer to the pipe wall. The transition zone from laminar to turbulent flow, that is a Reynolds number range between 2,320 and 4,000, is very unstable. And due to this, errors of up to 33% can occur, so measurements should preferably be performed with turbulent flows. Turbulent flow profiles more or less fill the whole cross-section of the pipe and do not show these differences. For ultrasonic flow meters with only one path, the typical accuracy for Reynolds numbers greater than 10,000, in other words with a clear turbulent flow profile, is 1 to 2%. We may ask ourselves, how can we get higher reproducibility and greater accuracy? Let's look again at what we actually measured before. That is, the average flow velocity V over the acoustic path, L. What we need in order to achieve the greatest possible accuracy is the flow velocity over the entire cross-section of the pipe, which is given here as V, average. If we now compare an ultrasonic flow meter with 3 paths, which is approaching the ideal measurement, one important advantage stands out immediately. 3 flow velocities, resulting from measurements at 3 different levels, all contribute to determining the average flow velocity. Since we're now receiving flow velocities at 3 different levels, Vm1, Vm2, and Vm3, the speeds of the 3 paths are averaged differently in the end result. With 3 paths, we receive more information about the flow profile. More accurate measurements can be made of non-symmetrical flow profiles, for example, downstream of pipe bends. There is enhanced reproducibility in a wide range of process conditions and a high degree of accuracy over the entire Reynolds number range. In this case, the accuracy is plus or minus 0.5%. We can compare the different ultrasonic flow meters with single or multiple paths. In a measuring device with a single path, the flow is only measured in the center of the pipe, so the measurement is dependent on the Reynolds number and is sensitive to non-symmetrical flow profiles. If the acoustic path fails, the entire measurement fails, as there is no redundant path. In the turbulent area, the accuracy is plus minus 1 to 2%. Ultrasonic flow meters with 3 paths give more reliable measurement results than flow meters with only a single path. Their dependency on the Reynolds number is less than 0.5%. With 3 paths, you correct for non-symmetrical flow profiles. If one path fails, there are still 2 paths available for the measurement. This is known as redundancy. Typical accuracy for a 3-path meter is plus or minus 0.5%. Even greater accuracy can be achieved with a measuring device with 5 paths. Ultrasonic flow meters with 5 paths are used in particular for calculations with custody transfer, where high demands are made on accuracy. Ultrasonic flow meters with 5 paths are virtually independent of the independent Reynolds number and correct not only non-symmetrical flow profiles, but also for swirl. Multiple paths lead to redundancy measurements, so that measuring can continue even after the failure of an acoustic path, for example, when there is too much air in the measuring tube. When we compare the different arrangements of paths, we can see that multiple parallel paths provide the most information about the flow profile, as the measurement is at different levels. Multiple crossed paths averages, but still the measurement is through the center of the pipe. In ultrasonic flow measurement, it is not only the number and the arrangement of the paths which are important. So is calibration. Every corner ultrasonic flow meter is quality tested, continuously and individually, during the entire production process. The final step in the quality assurance procedure is flow calibration. Ultrasonic flow meters are dynamically calibrated under reference conditions. Water, 20 degrees C, 1 bar pressure, 10 dN straight inlet run, and 5 dN outlet run. Calibration of smaller diameters is on a piston prover. Intermediate sizes on a master rig, a closed-loop circuit with pumps and a reference meter to compare the meter under test, and the biggest diameters on a calibration rig with a high water tower. Let's go on to study the construction of a piston prover in more detail. We can split calibration according to diameter into 3 categories. The piston prover from DN 2.5 to DN 150, the master rig from DN 200 to DN 300, and from DN350 to DN3000 ultrasonic flow meters are calibrated using a calibration rig with water used as a calibration liquid, because changes in the characteristics of water due to pressure are negligible, and the effects of temperature differences are well known. Flow meters are calibrated under reference conditions, whereby the inlet and outlet runs, as well as the minimum and maximum flow rates, can differ from calibration facility to calibration facility. To obtain a stable flow profile, every calibration facility includes a flow straightener. With the piston prover, a known volume of water is pressed through the meter under test. This is performed via a dedicated calibration automated system. When the calibration has been completed successfully, a calibration certificate is issued. There are two critical parts of the piston prover: the diameter of the cylinder and the position of the piston which displaces the water. The movement of the piston is determined by a ruler mounted on the piston rod. The volume displaced through the piston is measured using the internal diameter of the cylinder and the movement of the piston. This volume is then compared with the volume which is measured by the meter under test. Calibration with a piston prover is possible up to a diameter of DN150. Bigger diameters are calibrated on a master rig or calibration rig. In general, the accuracy of a calibration rig must be 10 times better than that of the meter under test. Normally, the performance of the flow meter is checked at two different volumetric flow rates. We're not going to study in detail the construction of a calibration rig or a master rig, but will concentrate instead on the sizing of ultrasonic flow meters. Let's summarize briefly what we've learned in this module. We've studied the construction and the functions of an inline transducer for measuring liquids and the important physical basics for the measuring principle. In liquid measurement, we've seen that in particular the Reynolds number, which describes the flow profile in the pipe, the viscosity and the density must all be taken into consideration in ultrasonic flow measurement. You're now acquainted with the various arrangements and number of measuring paths, and can list the most important advantages and disadvantages and measuring accuracy levels. Finally, we looked in detail at calibration. In the third part, we will continue with the sizing of an ultrasonic flow meter for liquids. Welcome to the third part of the Corner e-learning course, Ultrasonic Flow Meters for Measuring Liquids in Closed Processes. To understand the subject matter better, you should have already completed the first two modules. We can now continue with the sizing of ultrasonic flow meters. But first, let's take a brief look at which other topics we will be dealing with in this final module. In this module, we will learn what must be considered when sizing an ultrasonic flow meter. You will also become familiar with the most important properties, advantages, and restrictions of ultrasonic flow meters for measuring liquids. You will find out what must be taken into account when installing ultrasonic flow meters, and last but not least, you will get to know the key industries and typical applications in which ultrasonic flow meters are used. So, now let's get started. Another question: how do you actually size an ultrasonic flow meter for liquids? What must be taken into consideration, and is there any help available? Generally, one can say that ultrasonic flow meters for liquids are easy to engineer. When the application conditions are known, the appropriate version of the flow meter can be determined very easily. The materials which come into contact with the liquid are all metal, so the material selection is easy. The cross-section of the pipe is unobstructed. Kohner's ultrasonic flow meter UFM 3030 can be checked using a sizing tool in Excel to see whether the ultrasonic flow meter chosen for an application is appropriate. We can look at a theoretical example. We have the following application. Minimum flow rate 140 liters per hour. Nominal flow rate 550 liters per hour. Maximum flow rate 12,000 liters per hour. Diameter DN 50 by 2 inches. Density 800 kilograms per cubic meter. Viscosity 1 centistoke. Medium crude oil. Here we can choose one of 3 different liquid groups. The correct group must be selected. Other details of this application example are maximum process temperature 25 degrees Celsius. Maximal process pressure 1 bar. Standard or other pressure classes can be selected. The material of the measuring tube is also standard. For example, a DN100 measuring tube of stainless steel. Other materials can also be chosen from the pull-down menu. We also choose standard for the flanges. For example, the material for flanges for DN100 is carbon steel. Other materials can also be chosen from the pull-down menu. We enter these data and then select the correct units from the drop-down menu. For example, at minimum flow, liters per hour. Below the input lines, there is a note about the parameter selected. For example, when the flow rate chosen is too low. However, in our example, measuring with the device is possible, since ultrasonic flow meters start measuring from nearly zero flow. So in this case, the note refers to the flow velocity that is outside its specification. 0.5 is less than V is less than 20 meters per second. That is too low. It is possible to compare different parameters in order to get the best possible sizing. To achieve an accuracy of 0.5%, the flow rate should be between 0.5 and 20 meters per second. On the right-hand side of the table under Output Flow Profile, the flow speeds and the Reynolds number are shown. In the field Output Flange Derating, we can see whether the device is sized correctly for the chosen materials. The maximum process pressure at nominal process temperature is given, as well as the maximum pressure class at maximum temperature. If needed, choose different materials for the measuring tube and the flanges and its pressure rating. A graphical view is shown at the bottom, in which the accuracy against the flow rate is illustrated. There is one thing we should not forget to mention at this point. In many process applications, the system uncertainty is influenced by not only the flow meter, but also by installed devices such as pumps, valves, etc. Let's look at an example with water. We enter the following application requirements in the sizing tool. Minimum flow rate 3.5 cubic meters per hour. Nominal flow rate 20 cubic meters per hour. Maximum flow rate 40 cubic meters per hour. Diameter DN50 by 2 inches. The density of water can always be entered as 1000 kilograms per cubic meter. Viscosity 1 centistoke. Medium water. Maximum temperature 80 degrees C. Maximum process pressure 2.5 bar. This example shows that even at 80 degrees C, the maximum pressure of this stainless steel construction is 36.6 bar. Let's move on now to the general properties and advantages of ultrasonic flow meters. Ultrasonic flow meters with full bore design and fully welded transducers have many advantages over conventional mechanical flow meters. The wetted transducers are non-intrusive. Ultrasonic flow meters have very high long-term stability. There are no moving parts, so there is no pressure loss, no wear and tear, and recalibration at a later date is not necessary. Another advantage is that because of the unobstructed pipe cross-section with its smooth surface, no deposits can build up. Ultrasonic flow meters are also ideal for bidirectional measurements. Unlike mechanical flow meters, the flow factor does not need to be changed. The measurement is the same in both the positive and the negative direction of the flow. The engineering of an ultrasonic flow meter is easy. No difficult choices of material selection for chemical resistance have to be made, because all wetted parts are made of metal. Nor does the electrical conductivity of the liquid play a role. Both conductive and non-conductive liquids can be measured. In other words, the meter is universal. Ultrasonic flow meters are easy to install and operate, and have a fast response time, which allows changing process conditions to be recognized quickly. Ultrasonic flow meters also have a wide measuring range. Measurement starts at nearly zero flow, up to 20 meters per second. Flow meters are relatively light, compact, and are completely welded. Flow meters also have the same diameter as the process pipe. As we've already seen, ultrasonic flow meters are ideal for universal liquid measurement, as they can measure both conductive and non-conductive media. Another feature that is unique for ultrasonic flow meters is the measurement of the velocity of sound that can be used for product identification or for diagnostic purposes. Whether the volumetric and/or the mass flow should be measured when fixed density is programmed. There are also special versions available, such as devices for high pressures or high temperatures. Besides the construction and the sizing of an ultrasonic flow meter, we need to know some facts to avoid the wrong applications. Partially filled pipelines result in the signal being unable to propagate sufficiently or at all in the medium, or the signal can simply not be measured at all, as the sensors are not wetted by the liquid being measured. Therefore, pipes should always be filled completely. Mixtures can be measured, for example, ethanol water or glycol water. Problems can, however, arise when mixtures are unmixable because of separate layers. One example of this is an oil-water mixture, where there can be reflections of the ultrasonic signal. Consequently, ultrasonic flow meters should only be used to measure homogeneous mixtures, or in other words, a single-phase liquid. Gas bubbles in the liquid can also cause measuring errors, as they produce signal reflections, and the volumetric flow cannot be measured correctly. As a rule of thumb, we can say that measurements are possible with less than or equal to 2 volume% of the gas bubbles in the liquid. One way to prevent gas bubbles is to increase the process pressure. The same effect occurs when there are solids in the liquid, as they can also cause reflections of the signal. The signal will not be reflected. As a rule of thumb, we can say that measurements up to 5% solids are possible. Also, the viscosity in liquids must also be taken into account. High viscosities lead to attenuation of the signal and can result in signal loss. The recommended upper value for the entire range of diameters is 100 centistokes. In practice, however, much higher viscosities are possible, but only after consulting the manufacturer. When installing ultrasonic flow meters, some instructions must always be observed. Ensure that the pipe is completely filled. Partially filled pipelines are not allowed, as they can give fluctuating or inexact readings. Avoid installations where gas can be present. Install, therefore, in the lower pipe bend, in a slightly uphill pipe, or in a vertical uphill pipe. Installation in front of an open discharge must be avoided, since a completely filled pipe may not be guaranteed. We can look at some recommendations more closely. In general, the following straight inlet and outlet runs must be respected during an installation. Upstream of an ultrasonic flow meter, at least 10 dN. The diameter of the measuring tube must be planned as the inlet run. The outlet run must be at least 5 dN. The distances are always measured from the flange. If there is not enough space to keep these distances, the longest possible inlet run should always be chosen. Shortening the inlet and outlet runs can, however, affect the measuring accuracy. The recommended value for ultrasonic flow meters is, if a straight inlet run is shortened by 2 dN, so it is 8 dN long, we must expect an additional measuring inaccuracy of 0.2%. In other words, 0.5% plus 0.2%, which gives a total measuring inaccuracy of 0.7%. After a T-piece, that is when two pipes intersect, a 10 dN inlet run must be used. Built-in flow control devices, such as control valves, can have multiple opening positions that may cause flow disturbance. So whenever possible, there should not be any valves installed upstream of the flow meter. Therefore, it is recommended to install the measuring device upstream of a control valve. If a shutoff device is installed downstream of the flow meter, an outlet run of at least 40 dN should be used. A pump should be installed upstream of the flow meter, with distance of greater than or equal to 15 dN to avoid pulsations. Also, avoid vibrations in the process. If vibrations should occur, a compact device must preferably not be used. Instead, install a remote version. Ultrasonic flow meters for liquids are used in a wide range of industries and applications. We can look at one or two examples, although this list by no means covers the whole range. One area is the chemical industry. Non-conductive media and media with very low conductivity, such as demineralized water, are easy to measure with ultrasonic flow meters and in all industries. Ultrasonic flow meters are also well suited to measuring all sorts of liquid hydrocarbons. Ultrasonic flow meters are used to measure raw products, intermediates, and end products. For example, in the chemical production of fertilizers and plastics during the process, where chemical products in the process have to be added or dosed. Urea, for example, is an important fertilizer which uses this process. Mixing naphtha and ammonia will give you urea. Other examples of chemical products are caprolactam, MDI, or liquid sulfur. The dosing of acids, alkaline solutions, and solvents can also be measured ultrasonically. For example, in the manufacture of plastics, such as polyethylene, polypropylene, or polymers. Ultrasonic flow meters are also in demand in the oil and gas industries, where they are used to measure crude oil when loading or offloading tankers, and when the oil is allocated to the tanks. As we've seen, the main advantage is that we can use the velocity of sound to distinguish between different products flowing through the same pipe system. Generally, ultrasonic flow meters can be found in all downstream processes, in other words, those processes in which hydrocarbons are measured, for example, in the transport pipelines of crude oil. Other key areas are petrochemicals and refineries, where ultrasonic flow meters are used in the allocation of refined products, crudes, naphtha, and many other liquid hydrocarbons. Ultrasonic flow meters are applied in several areas of energy production. The flow measurement of thermal oil, which is also known as heat transfer fluid in solar power stations or parabolic trough power plants. As ultrasonic flow meters provide high measuring accuracy in combination with negligible pressure loss, power plant operators employ them mostly for measuring thermal oil, which can have temperatures of up to 400 degrees Celsius. Ultrasonic flow meters are used in the cooling water circuits of power plants. This is demineralized water, which can be very effectively measured with ultrasonic technology. A third field is in the distribution of hot water from power station to customer for heating buildings. This is called district heating. In a distribution station, hot water is released into smaller networks. The flow and temperature are measured. When the water flows back into the power station, the temperature is measured again and the quantity of heat calculated. Ultrasonic flow meters are used in numerous processes in which steam is produced from demineralized water with its very low conductivity. The condensation from the boiler is also measured. Ultrasonic flow meters are used in water and wastewater industry. In desalination plants, which work on the principle of reverse osmosis, the pure water has almost no conductivity and the pressure rating can be quite high. Also, with ultrasonic flow meters measurement, there are no pressure losses which might affect the process. Another application is a wastewater treatment plant, where large nominal pipe diameters are required. In many industries, ultrasonic flow meters are built into cooling water circuits. Water is often pumped from a river, created and purified, and used as cooling water. Again, ultrasonic flow meters are used to measure hot or heated water too, such as in district heating. In conclusion, we can summarize briefly what we've learned in this module. Our first step was to discuss calibration and the sizing of ultrasonic flow meters. You've also gained an overview of the important properties and advantages of inline ultrasonic flow meters for liquids, while also knowing the restrictions of this measuring technique. We've seen the most important installation instructions for ultrasonic flow meters in liquid applications, and we closed by considering the industries and the typical applications for inline ultrasonic flow meters for liquids.